Dear students, welcome to EPG Pathshala. Today's module is on solar photovoltaic system. Majority of our energy requirement is in the form of electrical energy. The solar radiation that reaching the earth can be used directly or it is converted to electrical energy. So in this conversion, the main technology used is photovoltaic technology. Ministry of New and Renewable Energy Sources promoted this PV technology throughout the country, especially in the rural areas, by the scheme of Jawaharlal Nehru National Solar Mission. And over the years, this PV technology, the photovoltaic technology has improved a lot. So in this module, we are going to discuss on the fundamentals of this photovoltaic system, what is the working principle of this system, what is a solar cell or PV module, what are the different types of solar cells, classification of PV module system, what are the factors that affects the performance of this PV module system, the defects occur in a solar cell, and we will also see how to calculate or how to find out the area that is required for these PV cells to install, and we will see the advantages and disadvantages of this PV technology. Let's start with principle of solar photovoltaics. So this solar photovoltaic works on the principle of photovoltaic effect. It is a process where two dissimilar materials in close contact produce an electrical charge when struck by light or other radiations. The word photovoltaic derived from Greek word phos, which means light, that is photon, and voltage, that the word voltaic derived from the word voltage. So the word volt is actually named after an Italian physicist, Alessandro Volta. So as the name says, it is a device which combines light and voltage to generate power. The light from sun composed of energy packets are known as photons. These photons contain energy corresponds to different wavelengths of the solar spectrum. The photons strike a photovoltaic cell. It may be reflected, absorbed, or pass through p-n junction. The photons falling on the device generates current, which is driven by a voltage that is termed as junction voltage to generate electrical power output at the terminals. Those materials or devices which are capable of transducing the energy from the photons to electric current are termed as photovoltaic materials. When light strikes the p-n junction, in which electrons are not free to move from n region to p region due to potential barrier, the light provides the energy, that is EMF, needed to free some electrons from the bound condition depending on absorption of solar energy. Free electrons cross the junction between dissimilar crystals more easily in one direction, making a negative charge on that side, resulting negative voltage. So a photon with short wavelength and enough energy can break free an electron from an atom in a photovoltaic material. If this electron passes through a nearby electric field, it can emerge as an electric current. This electric current is a direct current which can be collected with the help of conducting bus bars. Normally, the source of this short wavelength photon is sun, and 47% of the sunlight contains energy in the visible photon range. Hence, more the sunlight or the photons falling on the photovoltaic material, more will be the current generated. And if there is no sunlight, that implies no current. That makes the photovoltaic process simple and facilitates direct conversion of light to electricity. So this is the principle of photovoltaic effect in the photovoltaic system. Let's see what is a solar cell. The solar cell consists of P-type silicon material, N-type silicon material, front metallic grid and an opaque black metal contact, opaque black metal contact. The bulk material consists of p-type silicon having thickness of 100 to 350 micrometer and a thin layer of n-type silicon having thickness of about 2 micrometer. It is diffused on this bulk material giving p-n junction. The metallic grid at the top of the cell is with n-type material and opaque black metal contact at the bottom of p-type material act as negative and positive terminals. What are the different types of solar cells? Depending on the type of material, the solar cell is classified as single crystal silicon cell, polycrystalline and amorphous silicon cell. Single crystal silicon cell, it is produced from silicon dioxide that is reduced to silica with 1% impurity. The efficiency is about 22%, but it needs high energy to produce and it is so costly. It also requires high radiation or high solar radiation for electricity generation. Polycrystalline silicon is directly, in the case of polycrystalline silicon cell, here the polycrystalline silicon is directly melted, doped with phosphorus and produced in desired shape and size. Amorphous silicon cells are produced using thin film technology. It has only a conversion efficiency of 4 to 8%. It is normally used in the for the indoor lights, pocket calculator, electronic watches and electronic instruments. Cadmium sulfide, cadmium telluride cells. It is also produced by thin film technology. The semiconductor, that is cadmium telluride, is vaporized and its film of 10 micrometer thickness is deposited on a thin layer of cadmium sulfide of 12 micrometer. This cell has an efficiency of 10%. Copper indium diselenide cell. It's a thin film polycrystalline cell that is made from copper indium diselenide and has an efficiency of 14%. Gallium arsenide cell. The cell has thin film of N-type and P-type gallium arsenide grown on a suitable substrate. It has efficiency of 20% with high cost of production. So the major types of solar cells are single crystal silicon cell and polycrystalline and amorphous silicon cell. The solar cell is a p-n junction with large surface area. The N-type material is thin for passing light through it and strike the p-n junction. The electricity is generated inside the depletion zone of the p-n junction when a photon of light is absorbed by one of the atoms in n region of silicon. It dislodges an electron from any atom, creating a free electron and a hole pair. This free electron and hole pair has sufficient energy to jump out of this depletion zone. If a wire is connected from the cathode at n-type silicon to an anode of p-type silicon, electrons flow through the wire. The electron is attracted to the positive charge of p-type material and travels through the external load, creating flow of electric current. So all the solar cells work under this principle. Let's see what is the energy of a photon. The energy of a photon is related to its wavelength by Planck's equation, that is E is equal to hc by lambda, where h is the Planck's constant with a value of 3 into 10 to the power minus 27 ergs, and c is the velocity of light, which is 3 into 10 to the power 8 meter per second. So if we substitute these values, we will get E is equal to 1.24 divided by the lambda. The difference between the conduction and valence band is called band gap energy. The photons having energy larger than band gap energy will be absorbed in the cell and will excite some electrons, creating electron hole pair. The photons with lower energy are wasted in thermal energy generation. Let's calculate the range of wavelength of solar radiation that is capable of creating electron hole pair in silicon having an energy gap of 1.12 electron volt. For this, we can use the solution as energy E is equal to hc by lambda, or you can simplify that as E is equal to 1.24 by lambda. Therefore, lambda is equal to 1.24 by the E. So, E value is 1.12. So, 1.24 divided by 1.12 will give you the lambda value, that is 1.11 micrometer. So, that is the range of wavelength of radiation that is capable of creating this electron hole pair. What is a solar PV module? A single solar cell has low output and no protection against dust, moisture, mechanical impacts and atmospheric harsh conditions. The suitable voltage and the adequate power can be generated by interconnecting a number of solar cells. This assembly of solar cell is called solar PV module. The solar cells are provided with transparent cover and are sealed for the assembly into module. Generally, a solar module has 32 to 36 solar cells connected in series. The power of module is the algebraic sum of peak power of individual solar cells. You can see in this figure, the solar, each one in this, the purple color is solar cell, while the entire one is solar PV module. This is about 36 solar cells. This PV module consists of 36 solar cells. Most of the photovoltaic materials use semiconductor materials to transduce the light energy to electricity. So, pure crystalline silicon, which is a group 4 semiconductor element, is one of the prominent and widely used material for photovoltaic technology. Let's see the physical structure of a photovoltaic module. It consists of 4 components, that are superstrate, photovoltaic device, polymeric encapsulant, or it is also known as potence, and the substrate. This is the schematic structure of this photovoltaic module. Here you can see there is a superstrate and you have a polymeric encapsulants and a substrate in it. And there is an interconnecting copper ribbon which is connecting the PV cells. The material and combinations used varies with respect to technology and applications. Let's see what is a superstrate. A superstrate material is normally a tempered glass with low iron content which has silicon oxide based anti-reflective coatings to minimize the reflections falling on the module. In some cases, fluoropolymers are also used. The size of a superstrate is in the order of 4 mm thickness. The superstrate helps the cells to avoid direct contact with the atmosphere and reduces reflection from the top surface. A superstrate must have high transmittance also. The photovoltaic device. Majority of the photovoltaic cells available in the market are silicon-based materials, which are laminated and sandwiched in the polymeric encapsulants. Average thickness of a PV cell is 0.1 mm to 0.2 mm. The photovoltaic cells are very sensitive and fragile. It can break into pieces if not handled properly. And the main function of the PV cell is to convert photon to electric power. Polymeric encapsulants. Normally, EVA, that is ethyl vinyl acetate, is used as a polymeric encapsulant with a thickness of 0.5 mm. The primary function of the encapsulant is to provide mechanical support, that is giving a proper adhesion, and physical protection, that is from weather and the other environmental factors, to the PV cells. It also acts as a good electrical insulator and optical coupler. For this, an encapsulant must have high dielectric breakdown and adhesion strength. It must be mechanically strong and resistance to break or tear. The material must have low moisture absorption and high resistance to UV. It should also provide good edge seal to the substrate. Now, what is the substrate? A thin multi-layered backsheet made of Tedlar or 0.1 millimeter thickness is used as a substrate in most of the modules that is available in the market. The substrate provides the required support to the module. It must be a good electrical insulator with strong adhesion. The Tedlar sheet must not allow any moisture, water or air to pass through the module. Some technologies use glass instead of this Tedlar, and this allows for the transparent PV structure. So, the photovoltaic module consists of superstrate, photovoltaic device, polymeric encapsulant and the substrate. Now, what is a solar PV panel? It consists of number of solar PV modules connected in series and parallel to get a power of desired voltage and the current. So, that means many solar cell form one PV module and many PV module forms one PV panel. When modules are connected in series, it is desirable that each module should produce maximum power at same current. So, this figure shows the series connected photovoltaic module. When solar PV modules are connected in parallel, it is desirable that each module should produce maximum power at same voltage. The parallel connection means both the terminals are connected to each terminal of other PV cell or the cell. This figure gives the parallel connected photovoltaic module structure. What is a solar PV array? A number of solar panels which are installed in an array field is known as photovoltaic array. The panels are installed as stationary facing the sun or installed with tracking mechanism. So, care is taken not to cast shadow on one panel by another one. What is solar efficiency? It is the ratio of maximum possible solar cell power output, that is Vm multiplied by Im, that is voltage and current, which is converted to solar energy supplied to the cell. So, efficiency is equal to the product of Vm and Im divided by the solar power. Now, what are the energy losses of solar cell? So, we have seen the highest conversion efficiency of a solar cell is about 24%, that is 20% and a little bit more. The following factors that lead to energy losses and that reduce the conversion efficiency of a solar cell are reflection losses from the cell surface, incomplete absorption, partial utilization of photon energy, collection losses, open circuit voltage, series resistant losses, thickness of cell. These are the major losses which reduce the conversion efficiency of a solar cell. Let's see a bit about the history of photovoltaics. In the year 1839, the French scientist Edmond Becquerel found that a voltage appeared when a metal electrode is illuminated in a weak electrolyte solution. It took another 40 years for Adam and Day to study the photovoltaic effects in solids. They built a small photovoltaic cell made of selenium whose efficiency was only 1 to 2%. And the industry which was more benefited by this invention was photography, as it helped them to make photometric light sensors. In 1923, Albert Einstein received Nobel Prize for his theoretical explanation of photovoltaic effect in 1904. At about the same time, in 1923, the Polish scientist Sokolski developed a method to grow perfect crystals of silicon, which was used later in 1940s and 50s to make the first generation single crystal silicon photovoltaic cell. In the beginning of 1960s, the cost was the inhibitive factor in the development of photovoltaic technology. But owing to its less weight and reliability, it was mostly used in satellites and spacecrafts for onboard power requirements. The technology became more efficient and comparatively cheaper by 1980s. and they were then used in various off-grid and lighting applications. The historical variation in the efficiency of photovoltaic technology is given in this figure. You can see the efficiency has improved over the time. Let's calculate the requirement of area of solar PV cells. Let's solve this with a problem. Considering solar radiation of 200 joule per meter square per unit time during daylight, find the area of PV cells needed to generate enough electric power to run a desktop computer using 400 watt, an electric geyser using 1 kilowatt, and a toaster using 500 watt. Assume the efficiency of photovoltaic to be 25%. So, the photovoltaic cell power output eta is equal to power output divided by solar power, that is 0.25, that is 25%, and the power output, that means they have already given the value of 200, so the actual power output is equal to 25% of 200, that is 550 watt, that is 50 watt. Now, the first one is a desktop computer. So, the power of the appliance, the power that is required by this appliance is 400 watt, and we have a power output of 50 watt. So, the area of PV cells is equal to 400 divided by 50, that is 8 meters square. And for the electric geyser, that power required of an electric geyser using the 1 kilowatt, that is the power required is 1000 watt, and the area of cells required is 1000 divided by 50, which gives 20 meters square. And for a toaster using 500 watt, the area of cells is 500 divided by 50, that is 10 meters square. So, the total load, you can add all the values of the power required, that is 400 plus 1000 plus 500, which give you 1900 watt, and the total area from the above calculations we have received. The area required for desktop computer is 8, electric geyser is 20, and toaster is 10 meters square. So, adding 8 plus 20 plus 10, we will get 38 meters square. So, this is the total area that is required by the desktop computer, electric geyser, and toaster for the PV cells for this power required. The types of defects in a PV module. The overall module reliability is determined by all the component materials, and the improper selection and design of the components can lead to various defects in PV module in its long-term field exposure. Some of the defects in PV module due to long-term exposure to the field are discoloration. You can see in this picture, these are normally seen in hot and dry zones because of the exposure of ultraviolet radiation and subsequent fading of the encapsulant. Another defect is delamination. It's a process of tearing or damage of lamination, mostly the encapsulant, due to extreme exposure to temperature, and these are normally observed in PV modules operating for more than 10 years. Another defect is corrosion. Normally occurs due to improper maintenance and non-cleaning of modules. It is normally seen in hot and humid zones, and the corrosion in the bus bars can increase the internal resistance of the cell and thus reducing the power output. Let's classify these solar PV systems. It is classified into central power system, distributed PV system, and hybrid solar PV system. So, in this central power system, the solar power stations is designed to meet high peak daytime load only and have large generation capacity, that is around 6 megawatt, and feed generated power into a national grid, that is central power system. Distributed PV system, this system are again subdivided into standalone system, grid interactive system, and small consumer system. Standalone system meant to meet electrical load of any remote area. like villages. The maximum power point tracker senses the voltage and current outputs from solar array and adjusts the operating point to maximum power output from the solar array as per climatic conditions. The solar output in direct current is converted into alternating current and fed to load. The energy storage is essential to meet the requirement during non-sunshine hours. Grid interactive system. This system met the requirement of house, village or installation first, and excess power is fed to an electric grid during the sunshine hours. Hybrid solar PV system is designed to provide electric power by other means like windmills, fuel cells and petrol or diesel generators beside this solar electricity. Advantages of PV system. It converts solar energy to electricity directly without the use of moving parts. The country like India, which is having about 300 clear sunny days in a year, that can be utilized for the energy. This solar energy can be utilized for energy production. So we can say the solar energy, the raw material for this PV system is abundant in our country. So it is one of the advantage, and it produces no noise. It is non-polluting, that is eco-friendly in nature, and it can be located near the point of load and requires distribution system. But the disadvantages of this PV system are high cost of installation, the efficiency is low, it requires large area of installation to produce sufficient power, it requires batteries to store energy during sunshine hours, and sometimes output is intermittent. And it is most useful in those areas which is receiving more sunshine hours throughout the year. Solar PV programs in India. Ministry of New and Renewable Energy started the PV programs like solar street lighting system, solar water heating systems, solar space heating system, solar lanterns, standalone type solar PV systems, hybrid solar PV systems. And they encourage this PV system within the country by the scheme of JNNSM, that is Jawaharlal Nehru National Solar Mission. The cost of PV module in India varies between 30 rupees and 60 rupees per watt of power generated. So over the coming years, the R&D will develop and this cost may again get reduced or it become most cost effective. So to conclude, in this module we have seen what is the principle of photovoltaic system. So it is based on the photovoltaic effect where two dissimilar materials comes in contact, and when a photon struck on it, it produces electric charge. And we have seen that single solar cell consists of N-type, P-type material. Silicon, especially the silicon material is used for this solar cell. But it has low energy. So the assembly of solar cell is used, that is known as the solar module, PV module, that is photovoltaic module. And the structure of PV module consists of mainly 4 components. These are the superstrate, the photovoltaic device, the polymeric encapsulants and the substrate. And we have seen that this PV modules are connected in series or in parallel to form the arrays, and this array which makes the panel. And we have also seen what are the different types of solar cells like single crystalline silicon cell, polycrystalline or amorphous silicon cell. We have seen that the efficiency has increased over the years due to the research and development in this technology. We have seen different the parameters that affects the performance of this PV module like the reflection losses and the absorption efficiency also play a role in the output, power output. We have seen the area to be calculated, the area that is required for the PV installation to meet the power requirements. We have seen that defects over the long run, some defects like the discoloration, delamination, and corrosion can happen to the solar cell. That is to be taken care of for its power output or improving the efficiency. We have seen some advantages as well as disadvantages of this PV technology. And the government has taken some measures, or the schemes are running to improve or to encourage the use of PV technology in our country. Thank you.